because of the cost implications. All PPIs have similar potencies, undergo fast-pass metabolism primarily by cytochrome 3A4 and cytochrome 2C19. All the PPIs are chiral because of the sulfur. Both isomers are converted into the non-chiral active species at the same rate. In vivo, the esomeprazole produced higher plasma concentrations because it undergoes less metabolism by cytochrome 2C19 and thus produces 70% higher area under the curve than omeprazole. That is just a summary. The mechanism of action we have done. I don't need to go back there. This is still this mechanism of action, but I see there are some factors there. The pKa and the hydrophobicity of the PPIs determine the extent to which it accumulates in the canalicular lumen. pKa, we have understood why. Because if it has high pKa 1 and 2, then the minute it gets in, it's protonated and it is trapped. Remember, if it's not protonated, it's not trapped. It can also move out, or it can move into other cells. But once it gets into the canaliculi or canaliculars, or it gets into the parietal cells, it is protonated, it is trapped. It cannot move anywhere. So that maintains its high concentration. Hydrophobicity, we know hydrophobicity will allow it to penetrate the lipid membranes. So that's why we are saying the pKa and the hydrophobicity of the PPIs determine the extent to which it accumulates in the canalicular lumen. The rate of enzyme inhibition corresponds to the rate of sulfonamide formation. That definitely, that we have already said. You require to have the sulfonamide, which is the active moiety, because that is the one which you combine with the enzyme. You require the drug to be in high concentrations. You require, of course, the drug to be in high concentration. You require it to be protonated for it to be able, first of all, to be protonated first, and then to undergo the equilibrium, and then to give you the moiety that attacks or that is required for activation. Factors that determine the therapeutic index of the PPI include the acid space. The acid space dependent concentration of the PPIs. All we are saying is acid space dependent concentration of the PPIs, that these drugs are concentrating within the acid area. So that the fact that they concentrate within the acid parietal cells, that contributes to their therapeutic index. They concentrate within the parietal cell, and the parietal cell is very close to where we have the receptor. pH-dependent conversion from the accumulated prodrug to the activated species that is highly reactive therapeutic reagent. So we are saying that within the canaliculi we have acid pH, and that acid pH will allow for the change, will allow for the conversion of these drugs to the active, either the sulfonamide or the sulfonic acid, and that is very important. So two factors that are important is the area, is the space, and this acid space is very near. The acid space or the area or the place where they are being converted into the active moiety, very near your receptor. Number two, the acidity within the canaliculi, which avails or allows for the protonation of these drugs. And once these drugs are protonated, they are trapped. And once they are trapped, they remain there. Once protonated, they undergo equilibrium. They give you the moiety you require for activation, because it is only the active moiety that can bind the ATPase enzyme. So if that area of the parietal cell is non-acidic, even if the drugs are in high concentration, they will not have any activity. So those two factors, pH-dependent conversion and also the acid space very near the site of action, are very, very important. The factors, these we have done. Factors that can influence, which are important in the activity of these drugs, are one, the unique location of the proton pump. We call it, of course, the proton, the hydrogen potassium ATPase, and the specific action of the PPI. So you have the unique location. So this unique location is very important. It is within the parietal cells, and within the parietal cells, that is where the activation, that's why we are calling it unique location, very near the area of activation of of the ATPase, of the hydrogen ATPase pump, or the hydrogen ATPase, hydrogen potassium ATPase enzyme. And then their specific action, in fact, the fact that they go for this specific enzyme, within this specific area, and therefore bring about a minimal toxicity. They have that unique location and they have their specific action. They have their specific action on activation of binding, especially the ones we call selective, apart from pantoprazole, which we say decreases selectivity, or meprazole and labeprazole are very selective for the ATPase enzyme, which is necessary for secretion of hydrogen ion into the lumen. So that specific activity is very important. The conversion, the concentration of the protonated from the PPIs in the acidic canaliculars, that is a trapping. It gives us enough concentration to allow for effective activity, or it will allow for good activity. The conversion of the PPIs in the acidic compartments close to their target enzyme. So again, this we have said it more than enough times. So the unique location of the enzyme, the specific action, the concentration of the protonated, and also the nearness, the closeness of the activation of the PPIs very close to the target enzyme. And now when they come to target that enzyme, there could be many other enzymes, but they specifically go for the proton potassium ATPase pump, which is responsible for secretion of the hydrochloric acid, and therefore reducing the hydrochloric acid in the lumen, and hence reducing the irritation which you could have from the acid. We had mentioned this. It has the lowest dependence of all PPIs on cytochrome isoforms for its biotransformation, and is primarily inactivated through non-enzymatic conversion. So this is just an addition of labeprazole that we are saying it has the lowest dependence of all the PPIs on the cytochrome iso enzyme. That's a cytochrome C19, C219, and also the 3A4. And we remember we mentioned that you can also have non-enzymatic metabolism or reduction of the thioether. If it is reduction, that means the oxygen is removed and it is replaced with the hydrogen to give the sulfite. The none that is non-enzymatic. No cytochrome-mediated drug-drug interaction involving labeprazole have been noted in the literature. So again, it's a very safe drug, very, very highly active, very, very safe, and that is a positive for that drug. I think we have mentioned metabolism. I doubt we need to go back to it. We already have mentioned different proton pump inhibitors depend differently on the cytochrome 2C19 for oxidative metabolism. Pantoprazole, meprazole, and lansoprazole show greater metabolism via cytochrome 2C19, but omeprazole shows the highest. Labeprazole, as we have just mentioned, is metabolized only to a small extent by the cytochrome P450 enzymes. We've already mentioned that. The enantiomers show variation in dependence on the cytochrome 2C19 and other pathways, principally cytochrome 3A4. A significant fraction of the dose is biotransformed in the gut and via fast-pass metabolism. In addition to the oxidative metabolites generated by the cytochrome P450 enzyme, isoenzyme, the sulfonyl group can undergo non-enzymatic reduction, the sulfite also called the thioether. So that is just a summary of what we have done. That we have already mentioned. Perhaps the only thing we have added is the fast-pass metabolism. No, of course, note the fast-pass metabolism is terrible because the drug is metabolized before it has even reached its site of action, and that is why we call it fast-pass metabolism. The drug is metabolized before it has brought about activity. But when you are, of course, considering the dosage, when the dosage is being calculated, the amount of drug that goes to waste through fast-pass metabolism is already catered for, not unless if the patient has other issues. So that is already catered for. So the dosage caters for that, so that whatever remains is enough to give you the activity that you require. Metabolism into sulfone, hydroxylated, or demethylated metabolites, that's what we have mentioned. You can get the sulfone, You can get the hydroxylated metabolites. You can get the old methylated metabolites, most of those, and then you can also get the sulfide, as we have already said. The cytochrome 3A4 contributes to a lesser extent compared to the cytochrome 2C19. Further oxidation of the sulfone affords additional metabolites which are excreted in the feces. Again, I think we have mentioned most of the metabolism. And that is now how we looked at this. And we are saying that is oxidative hydroxylation, cytochrome 2C19, and again, oxidative O demethylation, mainly cytochrome 2C19. The main one, which is cytochrome 3A4, not a major route, is self-oxidation. And we have also said non-enzymatic, especially for abeprazole, where this S double bond O is converted to SH and through a reductive metabolism. Stereochemistry, I think we have just about to finish. Stereochemistry and metabolism. And we did mention, because of the presence of the sulfoxide, these drugs have a chiral sulfur atom. Stereochemistry has an effect on the pharmacological and depositional characteristics. And indeed, we did say esomeprazole is metabolized lesser by the cytochrome 2C19. That's all we are highlighting here. The oxidative metabolism of omeprazole is catalyzed principally by the cytochrome 2C19, primarily the 5' hydroxylation, and to a lesser extent, the benzimidazole or demethylation. In human liver microsomes, the R positive enantiomer is cleared more rapidly, and it is almost exclusively metabolized by the cytochrome 2C19. The R positive is the omeprazole. So the R positive is the omeprazole is a racemic mixture. It will have the R positive and it will have the S negative. And that is why the R positive innate will be metabolized much faster, reducing the dosage and therefore lesser activity. The clearance of the S minus enantiomer is more dependent on oxidation by cytochrome 2C19 than on cytochrome 3A4 mediated metabolism, primarily sulfone formation. So in humans, the R positive enantiomer is cleared more rapidly, and it's almost exclusively metabolized by cytochrome 2C19. So that is a very important point, because there is differential metabolism depending on stereochemistry. And because of that differential metabolism, which is anchored on stereochemistry, then you find one drug being more potent, or having longer duration of activity, being more potent than the other, because it will be more available. And we're also seeing the clearance of the S enantiomer is more dependent on the oxidation by cytochrome, and then on that mediated primarily the sulfone formation. The marketed single enantiomer, esomeprazole, provides one greater bioavailability in those who are cytochrome 2C19 extensive metabolizers. So it gives them a greater bioavailability. Two, it also gives less, so because we have said the esomeprazole, or the esomeprazole, which is the E isomer, has lower rate of metabolism than cytochrome 2C19. So by cytochrome 2C19. So if you have people who are extensive metabolizers, if you give them esomeprazole, they will still metabolize. Using the cytochrome 2C19, they will still metabolize the esomeprazole much more lower than omeprazole. If you give them omeprazole, because of the R positive enantiomer, which is more metabolized by cytochrome 2C19, they will clear the whole of it very fast, and therefore there will be very low bioavailability. So we are only saying because the esomeprazole is lesser metabolized than by cytochrome C219 than the omeprazole or than the R isomer, it gives higher bioavailability in those who have those isoenzymes. You know, there are patients who are extensive metabolizers, others who are slow metabolizers, and those are susceptible to very high drug drug toxicity, depending on what they are. Either they can get drug toxicity or they can have drugs that do not have any activity, because if you're an extensive metabolizer, it means when you get that drug, you metabolize it very quickly, and therefore the standard dose, which is expected to give you a pharmacological activity, does not give you pharmacological activity, because its bioavailability will be highly negatively influence. And that's all we are saying. There will be less inter-individual variation in those who are cytochrome 2C19 poor metabolizers. Again, because there is a balance, the esomeprazole gives a balance on the metabolism of the cytochrome 2C19. Even those where you have less inter-individual variations, you will also not have a problem. The impact of variant alleles of cytochrome 2C19 is less on the esomeprazole enantiomer than on the parent race mixture. It's because of the fact that the cytochrome 2C19 metabolizes the esomeprazole much lower than the impact. So when you talk about alleles, these are people who have different types of the cytochrome 2C19, not whereby some of them are faster metabolizers than others. Remember, the rate of metabolism is dependent on these enzymes. So their enzyme, their cytochrome 2C19 have some slight difference either in the sequencing or in their arrangement of the amino acids. So that slight difference in their cytochrome 2C19, that's what gives the allele. All alleles are those different forms, different isoenzymes of the same enzyme, whereby they give polymorphism, whereby you have some people who are fast metabolizers, you have others who are slow metabolizers. So you're saying the impact of the variant areas of cytochrome 2C19 is less in when you take the esomeprazole compared to the parent race mixture. And this is only because the esomeprazole, which is the S enantiomer, is less metabolized by the cytochrome 2C19 compared to the R positive. So that slow metabolism by the cytochrome 2C19 now allows that even those who have variations within themselves in their metabolism of this drug, there is a bit of control, because their rate of metabolism, when you give that drug, its rate of being metabolized by the cytochrome 2C19 is much reduced. Because it's much reduced, any other effect caused by the variation of the enzymes will not have a very big impact, like when the rate of metabolism by that particular enzyme is very fast. So that it's like a balancing act. The rate of metabolism by that allele is already reduced, and therefore, even if you have another influence by the alleles or by whatever it is, then the effect will not be too major, and hence the inter-individual variation and even the bioavailability will not be highly influenced or will not be highly compromised. I think that was the last slide for the PPIs. So looked at quite a number of aspects of the PPIs. We have never looked at any activation of any prodrug, but with the PPIs, we are able to look at the activation of the PPIs. This is just now summary. Then remember, we did mention the prostaglandins are also used as anti-ulcers. They have anti-secretory effects on gastric acid. They inhibit adenyl cyclase activity in the parietal cells, which results in secretion of gastric acid. They stimulate secretion of mucus and bicarbonate in adjacent superficial cells. We're also saying the prostaglandins, we have said that they are also used. You can also collect, like remember we did mention misoprostol, mixing misoprostol with diclofenac, because we know diclofenac will have bring about gastric irritation, and you can reduce that gastric irritation by combining a prostaglandin with an non-steroidal or anti-inflammatory, and we did explain why. So we are only saying prostaglandins can also be used as anti-ulcer drugs. They will inhibit the adenyl cyclase activity in the parietal cells, and remember that adenyl cyclase activity is important in and acid secretion, especially stimulated by histamine. The endogenous E series prostaglandin and other more stable synthetic cogeners have cytoprotective effects. For example, misoprostol. So we are saying the E series, prostaglandin E series, the E2 series. But of course, we did mention the endogenous prostaglandins have a big problem in that they are not orally active. So you require structural modification to give molecules or to give groups or to give prostaglandins that are orally active. And that is how we were able to discuss misoprostol, because misoprostol has structural modification that allows it to have stability and allows it to have activity. We had already mentioned this, and this is a drug. We had mentioned it. If you look at it, almost all the endogenous prostaglandins, and you can see this prostaglandin E1 series, it has a hydroxyl group at position number 15, 12, 13, 14, 15. You can see misoprostol, so that you decrease that metabolism at position number 15. You have shifted the 15 hydroxyl group to position 16 with retention of good activity. Again, if you look at prostaglandin E1, it has a carboxylic group at position number 1, but in misoprostol, you have an ester. The ester gives a bit of stability. The ester is also not ionized. Misoprostol is ionized, therefore absorption very poor. This is an ester. It has slightly higher lipid solubility. Of course, it can undergo hydrolysis through esterases enzymes, but at least it has higher lipid solubility. It has much higher stability, and therefore better absorbed, has better stability within the body, and therefore this drug can be given orally mixed with the prostaglandins. But do remember, we didn't mention misoprostol can cause abortion. It can cause contraction of the smooth muscles, including the uterine muscles, and therefore to whom you give, you must be careful. Otherwise, it can cause you devastating effects. And we have already said, you can see a combination of diclofenac. This is something we have done. Fortunately, we have looked at this, but we must be careful that it is associated with abortifacient properties, and that is contraction of the smooth muscles, and it can also cause diarrhea and abdominal pain, also effective in cervical ripening, and therefore it can induce labor. So that we must be careful. It has good effects. You can combine it with some of the non-steroidal anti-inflammatories, especially if you have to give the non-steroidal anti-inflammatories to patients who are highly susceptible to ulcers. Then you can combine the non-steroidal anti-inflammatory with a prostaglandin. But of course, you must understand, you must take your history carefully so that you know exactly who you are giving the drug. And I think that will be the end of those drugs. What's the time? Well, tunachoka kabisa. 13:22. What time did we start? I think we have. Now, the only other very small bit that we haven't looked, I said I left this out. The structural characteristics of the prostaglandins and the nomenclature. I left it out because I had given you an assignment. But this is very straightforward from what we have done. I think I can post you this. You are only saying general structures. You must have that hydroxyl group. You have that 5-alpha hydroxyl group, if you remember. You have the 2 side chains. Unless if you have a double bond here, like in the prostaglandin B, then this and this are trans to each other. So we're only looking at the general characteristic. It must have a 15 hydroxyl group. This is in the naturally occurring prostaglandin, and we are saying not unless if you have a double bond at position 8-12, then the 2 side chains are trans to each other or have trans stereochemistry, not unless if you have a double bond at that position. Then the classification, I believe you read about this when you are doing your assignment. Of course, you classify them and you give them the capital letters A, B, C, D, E, F, G, H, I, J, up to K. And of course, that's why we have been talking about prostaglandin A, prostaglandin B, prostaglandin E. So the name gives you the type of prostaglandin. So prostaglandin A, prostaglandin B, prostaglandin D, and so on. Example, you can have, say, prostaglandin A. Now, when you say prostaglandin A is dependent on the substituent that is found in position 9 and position 11. That is what determines which prostaglandin it is. So classification depends on the nature, the type, and stereochemistry of the oxygen substituent at position 9 and 11. Nature means at that position 9, you can have a ketone, and position 11, you can have a hydroxyl group. At position 11, 9, you can have an hydroxyl group, and at position 11, you can have a ketone. You can just have one ketone. So that's what we are talking about, the nature. What group do you have? Stereochemistry. Most of them have an alpha orientation. Like when you talk about prostaglandin F, 2 alpha. That alpha means that when you look at prostaglandin F, it has a hydroxyl group at position number 9 and a hydroxyl group at position number 11. The alpha is what tells you that the hydroxyl groups have an alpha orientation. You can have PGF beta down there. If it is beta, it means the hydroxyl group has a beta orientation. So we are only saying that the name, when you mention the name of a prostaglandin, you already know which group you have at position 9 and at position number 11. So and you look at the examples, this is just emphasizing on the same. And we look at the examples. That is the same thing which I've said, that if you're talking about PGE is because you have a ketone at position 9 and you have a hydroxyl group, alpha hydroxyl group at position number 11. When you look at PGF, you have an PGF alpha. That means there's an alpha there. You have an alpha hydroxyl group at position number 9 and an alpha hydroxyl group at position number 11. If you talk about the PGG series, and of course, then you have the endoperoxide. So PGG series, you have the endoperoxide at that position number 9 and number 11. So we are only saying that the name that is given to the prostaglandin is dependent on the substituents that you have at position number 9 and position number 11. We say that they are derivatives of the hypothetical compound prostanoic acid. Prostanoic acid does not exist. In the approved nomenclature, each prostaglandin is named using the prefix PG. So all of them are PG, followed by a letter A to K, depending on the nature, position, and stereochemistry of the substituent on the ring. So you have said, depending again on the nature, the position, yeah, because the nature is important. Which position, which group is in position 9, which group is in position 11, and the stereochemistry, is it alpha or beta, to give us the prostaglandin F2 alpha. And even for the prostaglandin E, the hydroxyl group must have the alpha orientation. The alpha designation refers to the stereochemistry of the hydroxyl group at carbon 9 below and on the same side Cs of the ring as the OH group at carbon 11. So the alpha, the hydroxyl group at position 9 carries an alpha, the hydroxyl group at position number 11 carries an alpha. That's when we say PG 2 alpha, OH group at position 9 alpha, OH group at position number 11 alpha. The number of double bonds in the side chain connected to the cyclopentane ring, that is given a subscript 1, 2, and 3, given the subscript 1, 2, and 3. And you remember, like we are talking about PGE1. PGE1, meaning you have a double bond between carbon 13 and 14 for PGE1. PGE2, you have a double bond, position 13, 14, position 5, 6, PGE2. Then you go to PGE3. So we are saying the subscript, which is also written, when you write the name of the prostaglandin, you will write that, put the letter, giving you the type of prostaglandin it is. You will add the subscript, telling you the number of double bonds, and of course, if where needed, you will write alpha or beta, but of course, mainly alpha, especially for PGF2 alpha, meaning it has 2 double bonds. It is an F, telling us it has a hydroxyl group at position 9 and position number 11, telling us that those hydroxyl groups are both carrying the alpha orientation. In other words, when you look at the name of a prostaglandin, it tells you the classification, the type, the class. It tells you the type of which class of prostaglandin is it. If you look at the structure, it will tell you, is it a, when you come to name the prostaglandins, you name them such that you know what type it is, what group is in position number 9, what group is in position number 11, what orientation are those group, position number 9 and position number 11, what are the number of bonds. So when you look at that short form, that condensed formula of the prostaglandin, you look at that name and you can be able to draw the structure, because the name PGD2 tells you exactly the exact structure of that prostaglandin. What is its type? Where which bonds? Where are the bonds? Which groups do we have at position number 9 and 11? And how many bonds does that prostaglandin have? And that's what we are calling the nomenclature. That in looking at the structure or at the condensed name of the prostaglandin, you can be able to draw the structure. So that is the prostanoic acid, is the hypothetical molecule, which we say the prostaglandins were named from, prostaglandins from the hypothetical molecule. And the hypothetical molecule is that molecule that is a 20 carbon molecule with no double bonds, but containing a cyclopentane ring, of course, with a carboxylic acid. That's the very, very basic. That's a very basic precursor for the prostaglandins. But as I have said, it's a hypothetical molecule. It does not exist. Then when we say PGE1, we are talking about that molecule which has a ketone at position number 9, an alpha hydroxyl group at position number 11, and it has one bond at position number 13, 14. We have said for all prostaglandins, for all endogenous prostaglandins, they will have a hydroxyl group. They will have a hydroxyl group at position number 15. So for all of them, they will have a hydroxyl group at position 15. So therefore, when you see PGE1, you can be able to draw the structure. When you talk about PGE2, the same thing. The only difference is that the 2 is telling us you have 2 double bonds, one at position number 13, 14, and the other one at position 5, 6. When you go to PG3, again, it is E. It has the same structure. The only difference is that you have one double bond. The first one, all of them, all the prostaglandins will have the bond at 13, 14, and then you go to 5, 6, and then you go to 17, I believe. 13, 14, 15, 16, 17. You go to 17, 18. So for prostaglandin 3 series, then you have an extra double bond at position 17. So that's what we are saying. If you're given the structure PGE2, you can draw it very easily. You can't be able to differentiate PGE1, PGE2, PGF, whatever it is, by understanding that nomenclature. The subscript 2 indicates additional. It's all that we have done. We don't need to go back to it. So if you have PG2, it's an additional. These bonds are cis to each other. An additional cis bond at position 5, 6, and a PG3, an additional cis bond at position 17, 18, as we have already talked about. So when you look at PGF2, it has 2 hydroxyl groups. Those are the same things. So that is just putting it in words, but we look at the structures so that what the words are saying is what we have here. So this is the finality of all that which we are saying. We are saying if you have PGA1, this group there and that group, they are the same for all the prostaglandins. So of course, with a slight exception with the prostacyclins. So that R1 and R2 are the same. So when you talk about PGA1, it has a ketone at position number 9. And therefore, because it has no substituent at position number 11, you must have a double bond. So it has a ketone at position number 9. When you talk about the PGA ketone at position number 9 and a double bond 9, 10 at position 10, 11. When you come to PGB, is the one we said, it has a double bond between position number 8 and 12, and therefore these two groups should not have any stereochemistry because of the double bond. So we did mention, unless you have a double bond at that position number 8 and 12, as in prostaglandin B, R1 and R2 should be trans to each other. So again, the ketone, you can see all of them, PGA1, PGB, PGC, all of them have a ketone at position number 9. What is changing is the position of the double bond. What is changing is the position of the double bond. Then you go to PGD. PGD is the opposite of PGE. So it will have a hydroxyl group at position 9 and a ketone at position number 12, number 11. So again, once you see PGD, you can't be able to do it. Then we go to PGE, again, a ketone position number 9, a hydroxyl group, of course, all beta position, both beta orientation and hydroxyl group at position number 11. That is PGE. Then we say PGF, alpha. This alpha signifies that group, and that group have the alpha orientation. The F signifies that there is a hydroxyl group at position 9 and a hydroxyl group at position number 11. Whether any of them is beta oriented is given by that small group, that small notation which is there. If it was beta, it means then there is beta orientation. PGG and PGH, of course, both of them carry the same. The difference is that in one having a hydroxyl group and the other one having a peroxide at position number 15. But what is of importance is that PGG and PGH, both of them will have the endoperoxide, and of course, giving us the precursors for the other prostaglandins. Then we have the PGI or the prostacyclin. And in the prostacyclin, we have introduction of the ether. Where one of the hydroxyl groups, alpha hydroxyl group, so it is actually a derivative of PGF. So one of the hydroxyl groups of position number 9 are joined through an ether linkage, because the hydroxyl group joins through an ether linkage to, this is position number, that is number 8, number 7, number 6. I believe this is number 6. So joined to the carbon number 6. So one of the oxygens of one of the hydroxyl group at position 9 is joined through an ether linkage to carbon number 6. And then, of course, here there will be a double bond and carbon number 5, and everything else continues. So same thing, it is similar structure. The only difference is, of course, that the prostaglandins are bicyclic. They are bicyclic with an ether formation, and the ether formation is from the hydroxyl group from position number 9, where it forms an ether linkage or an ether linkage with the carbon at position number 6. Then you have the PGJ. Again, the PGJ now, if you look at the PGA, PGB, PGC, the ketone is at position number 9. With PGJ, the ketone is at position number 11, and the double bond between 9 and 10. So it's just a reversal of what we have in PGA, B, and C, where the ketone now goes to position number 11, and of course the double bond, because there is no substituent at position number 9, there must be a double bond at position number 9. PGK is where now both groups are ketones. Both groups are ketones. So what we are saying, if you are given PG, draw the structure of PGK2, you will know you put a ketone in position number 9, you put a ketone in position number 11, and then you put 2 double bonds. You remember to put a hydroxyl group at position number 15. Then the thromboxanes. The thromboxanes again are also endoperoxides. They have the oxane ring, whereby they have oxygen as part of the 6-membered ring. So they have that oxygen there, and they have the endoperoxide. Again, that is the difference. The 2 rings are the same. So you can have, of course, the main one we have is thromboxane A2, which means, again, it has 2 double bonds at position number 13 and at position number 5. The only difference is that ring. Again, and indeed, the nomenclature is dependent on that ring. So when that ring changes and it becomes an oxane and it's an endoperoxide, then we have thromboxane, the thromboxane A. Thromboxane B is just the reduction or the removal of the endoperoxide. So removal, you can see that endoperoxide, and of course replace. So removal of the endoperoxide and replacement of the same with alpha or with 2 hydroxyl groups, and of course everything else remains the same, but the thromboxane B has no activity. It's a metabolite. Thromboxane B is a metabolite of thromboxane A, and it's only thromboxane A which has activity. Thromboxane B does not have any activity. So when we look at that, what we have discussed, when we look at, we understand what we have discussed, a group at position number 9, group at position number 11, a group at position number 15 for all of them, then a double bonds position, then that we have discussed, we'll have known the nomenclature, we'll have known the classification and nomenclature of the prostaglandins. I think that was what I had not discussed, because I had asked you to discuss it or to say something about it in your assignment, and most of you did it correctly. So I think with that, unless if you tell me so, I doubt I have anything else I have not discussed. Any questions?